Dear students, today we are going to talk about the fundamentals of factor analysis. And after talking about this, we'll try to understand that what exactly factor analysis is, what are the methods that we use for factor analysis, and what are the basic mathematical operations that underlie factor analysis. We will also look at the merits and demerits of factor analysis and the situations in which you can use factor analysis and the others in which you should not use factor analysis. Introduction. Factor analysis is one of those techniques that is used by a lot in the social sciences. When I say social sciences, it is used by the educators, by the psychologists, the political scientists and the sociologists, etc. Now, educators and psychologists have used factor analysis to understand how different kinds of people perceive different stimuli, and then they categorize them according to the different types of response sets that they get to these kinds of stimuli. Political scientists have used factor analysis basically to define and differentiate between different nations. Now, these nations are differentiated based on their political dimensions, the size of that nation and the wealth that that nation has. Sociologists have classified clique groups. Cliques, when I say, they are small groups of 2 to 3 people. They are based on the classification of different people on how they associate frequently with certain groups in comparison to others. Now, this module aims at defining the rationale of factor analysis, understanding the relationship between factor loadings and correlation coefficients, the mathematical operations that underlie factor analysis. These mathematical operations, they include relationship of correlations, the variance and the covariance to the factor module. We are also going to talk about when and when not to use factor analysis. What are the situations which are not suitable for using factor analysis?
What is factor analysis? Factor analysis refers to a set of statistical procedures to locate a small number of clusters or factors in a large set of independent variables. Factor analysis may be exploratory or confirmatory. Exploratory factor analysis attempts to reduce a large set of variables into a smaller set by identifying variables that have high correlations with each other and are categorized as representing a single factor, and variables that do not correlate with each other are identified as representing orthogonal or independent factors. Confirmatory factor analysis posits that there are a certain number of factors for a set of given variables and then seeks to determine whether this hypothesis is to be accepted or rejected. In this module, we will primarily be focusing on exploratory factor analysis. According to Reber and Reber, an ideal factor analysis would identify a small number of factors which are orthogonal to each other. That is, in spatial terms, they would lie at right angles to each other when graphed. The basic data used for factor analysis is same for the correlation matrix when using the different procedures of analysis, though there may be procedures that make use of the matrix of covariance. The major methods of factor analysis used are centroid method, developed by Thurston in 1947, the summation method by Burt in 1941, principal axis method by Kelly in 1935, and principal components method by Hotelling in 1933. Correlation coefficients and factor loadings. The method used for factor analysis in this module would be Thurston's centroid method. In this method, the correlation matrix is replaced by the factor matrix statistically. In a correlation matrix, the number of rows and columns is the same consisting of correlational values. These values range from -1 to +1. On the contrary, the number of columns is usually less than the number of rows in the factor matrix. The columns represent the common factors and the row values are the factor loadings ranging from -1 to +1. If the factors are orthogonal, then the factor loadings are correlational coefficients of the test with the factors. But if the factors are oblique, that is correlated, then the factor loadings may or may not be the correlations between the tests and the factors. To obtain a correlation matrix from a factor matrix, let us understand the multiplication of two matrices. Suppose there is a factor matrix F where factor 1 has the variables x1, x2 and x3 and factor 2 has variables y1, y2 and y3. By interchanging the rows and columns of the matrix, we get a transpose of this matrix which is F dash, where F dash is equal to x1, y1, x2, y2 and x3, y3. If R is a correlation matrix, then mathematically R is equal to F into F dash. Thus, F into F dash is equal to factor matrix 1, which is x1, x2, x3 and y1, y2, y3 multiplied by F dash matrix, which is x1, y1, x2, y2, x3, y3, which is equal to the correlation matrix R. Therefore, the correlation matrix R is equal to x1, x1 plus y1, y1, x2, x1 plus y2, y1, x3, x1 plus y3, y1, column 2, x1, x2 plus y1, y2, x2, x2 plus y2, y2, x3, y2 plus y3, y2. Column 3 is x1, x3 plus y1, y3, x2, x3 plus y2, y3 and x3, y3 plus y3, y3. One has to be careful while calculating the correlation matrix as F into F dash is not the same as F dash into F. Therefore, mathematically, F into F dash is not equal to F dash into F. For a factor matrix with three factors, suppose there is a factor matrix F in which factor 1 is x1, x2, x3, x4 and x5, factor 2 is y1, y2, y3, y4, y5 and factor 3 is z1, Z2, Z3, Z4 and Z5. By interchanging the rows and columns of the matrix, we get a transpose of this matrix F dash which is equal to x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4 and x5, y5, z5. If R is a correlation matrix, then mathematically R is equal to F into F dash. Thus, F into F dash is equal to x1, x2, x3, x4, x5, y1, y2, y3, y4, y5, z1, z2, z3, z4, z5 multiplied by x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4, x5, y5, z5, which will be equal to the correlation matrix R. Therefore, R is equal to x1, x1 plus y1, y1 plus z1, z1, x2 x1 plus y2 y1 plus z2 z1, x3 x1 plus y3 y1 plus z3 z1, x4 x1 plus y4 y1 plus z4 z1, x5 x1 plus y5 y1 plus z5 z1, x1 x2 plus y1 y2 plus z1 z2, x2 x2 plus y2 y2 plus z2 z2, x3 x2 plus y3 y2 plus z3 z2, x4 x2 plus y4 y2 plus z4 z2, x5 x2 plus y5 y2 plus z5 z2, x1 x3 plus y1 y3 plus z1 z3, x2 x3 plus y2 y3 plus z2 z3, x3 x3 plus y3 y3 plus z3 z3, x4 x3 plus y4 y3 plus z4 z3, x5 x3 plus y5 y3 plus z5 z3, x1 x4 plus y1 y4 plus z1 z4, x2 x4 plus y2 y4 plus z2 z4, x3 x4 plus y3 y4 plus z3 z4, x4 x4 plus y4 y4 plus z4 z4, x5 x4 y5 y4 plus z5 z4, x1 x5 plus y1 y5 plus z1 z5, x2 x5 plus y2 y5 plus z2 z5, x3 x5 plus y3 y5 plus z3 z5, x4 x5 plus y4 y5 plus z4 z5, x5 x5 plus y5 y5 plus z5 z5. The correlation coefficients in parentheses are the communalities. The correlation matrix R thus obtained is a reduced correlation matrix as it contains the communalities of the test. This leaves behind the specificity and error variance of the test. If the specificity and error variances are introduced in the correlation matrix, then these cells can be assigned the value 1. In similar ways, the correlation matrix can be obtained for more than 3 factors. Illustration. Consider the following data: test A, B, C, D, and E. The corresponding factor loadings are: for factor 1, 0.7, 0.8, 0.2, 0.5, 0.1; factor 2, 0.1, 0.2, 0.7, 0.6, 0.8. The factor matrix for the above data is F is equal to matrix zero point 0.7, zero point 0.8, zero point 0.2, zero point 0.5, zero point 0.1, zero point 0.1, zero point 2, zero point 0.7, zero point 0.6, zero point 0.8. Thus, the transpose of the factor matrix is F dash, which is equal to matrix zero point 0.7, zero point 0.1, 0 0.8, 0 0.2, 0.2, 0.7, 0.5, 0.6, and 0.1, 0.8. The correlation matrix R is equal to F into F dash, which is equal to 0 0.7, 0 0.8, 0 0.2, 0 0.5, 0 0.1, 0 0.1, 0 0.2, 0 0.7, 0 0.6, 0 0.8 multiplied by matrix 0 0.7, 0 0.1, 0 0.8, 0 0.2, 0 0.2, 0 0.7, 0 0.5, 0 0.6, 0 0.1, and 0 0.8. R is equal to matrix 0 0.7 into 0 0.7 plus 0 0.1 into 0 0.1, 0 0.8 into 0 0.7 plus 0 0.2 into 0 0.1, 0 0.2 into 0 0.7 plus 0 0.7 into 0 0.1, 0 0.5 into 0 0.7 plus 0 0.6 into 0 0.1, 0 0.1 into 0 0.7 plus 0 0.8 into 0 0.1, 0 0.7 into 0 0.8 plus 0 0.1 into 0 0.2, 0 0.8 into 0 0.8 plus 0.2 into 0.2, 0.2 into 0.8 plus 0.7 into 0.2, 0.5 into 0.8 plus 0.6 into 0.2, 0.1 into 0.8 plus 0.8 into 0.2, 0.7 into 0.2 plus 0.1 into 0.7, 0.8 into 0.2 plus 0.2 into 0.7, 0.2 into 0.2 plus 0.7 into 0.7, 0.5 into 0.2 plus 0.6 into 0.7, 0.1 into 0.2 plus 0.8 into 0.7, 0.7 into 0.5 plus 0.1 into 0.6, 0.8 into 0.5 plus 0.2 into 0.6, 0.2 into 0.5 plus 0.7 into 0.6, 0.5 into 0.5 plus 0.6 into 0.6, 0.1 into 0.5 plus 0.8 into 0.6, 0.7 into 0.1 plus 0.1 into 0.8, 0.8 into 0.1 plus 0.2 into 0.8, 0.2 into 0.1 plus 0.7 into 0.8, 0.5 into 0.1 plus 0.6 into 0.8, 0.1 into 0.1 plus 0.8 into 0.8. Therefore, R is equal to 0.5, 0.58, 0.21, 0.41, 0.15, 0.58, 0.68, 0.30, 0.52, 0.24, 0.21, 0.30, 0.53, 0.52, 0.58, 0.41, 0.52, 0.52, 0.61, 0.53, 0.15, 0.24, 0.58, 0.53, 0.65. The correlation coefficients in parentheses are the communalities. Mathematical operations underlying factor analysis. To understand the mathematical operations underlying factor analysis, we first need to understand and define the following terms. Common variance is a portion of the reliable variance that correlates with other variables. Specific variance is the portion of the reliable variance that does not correlate with any other variable. Error variance is the chance variance due to errors of sampling, measurement, unstandardized conditions of testing, physiological and other changes within the individual, and other influences that contribute to unreliability. Error variance is assumed to be uncorrelated with the reliable variance. Uniqueness of a variable is the portion of the total variance that does not have anything in common with any other variable. As per the factor model, the total variance of any variable or test can be differentiated into three independent components vis-a-vis common variance or communality, specific variance or specificity, and error variance. Mathematically, total variance is equal to common variance plus specific variance plus error variance. Error variance is the standard error of measurement squared as per the reliability theory. Therefore, reliability is equal to 1 minus error variance. Error variance is equal to 1 minus reliability. As total variance is 1, from the above equations it can be said that 1 is equal to communality plus specificity plus unreliability, or 1 is equal to communality plus specificity plus 1 minus reliability. Therefore, reliability is equal to communality plus specificity. In most of the factor analysis, specific variance or error variance are grouped together as a unique variance or uniqueness. Hence, total variance is equal to communality plus uniqueness. 1 is equal to communality plus uniqueness, or uniqueness is equal to 1 minus communality. Communality is defined as the proportion of factor variance in the scores and is the square and sum of the factor loadings over a particular test. Similarly, the square and sum of the factor loadings over a factor is termed as the eigenvalue. In conclusion, it can be said communality, specificity, and uniqueness are measured for the test, whereas the eigenvalue and variance, that is percentages, are computed for the factors. Illustration: find the communality, specificity, and uniqueness for each test and the eigenvalue and percentage of variance for each factor from the factor matrix given. For test 1, 2, 3, 4, and 5, factor 1 is 0.7, 0.5, minus 0.30, 0.09, 0.11. For factor 2, 0.12, 0.30, 0.16, 0.17, 0.01. Factor 3, 0.09, 0.25, 0.50, 0.6, 0.7. Reliability is 0.70, 0.69, 0.99, 0.43, 0.53. Communality is equal to square and sum of factor loadings over each test. Communality of test 1 is equal to 0.7 square plus 0.12 square plus 0.09 square, which is equal to 0.49 plus 0.0144 plus 0.0081, which is equal to 0.51. Communality of test 2 is equal to 0.5 square plus 0.30 square plus 0.25 square, which is equal to 0.25 plus 0.0900 plus 0.0625, which is equal to 0.40. Communality of test 3 is equal to minus 0.30 square plus 0.16 square plus 0.50 square. This is equal to 0.0900 plus 0.0256 plus 0.25, which is equal to 0.37. Communality of test 4 is equal to 0.09 square plus 0.17 square plus 0.6 square, which is equal to 0.081 plus 0.0289 plus 0.36, which is equal to 0.39. Communality of test 5 is equal to 0.11 square plus 0.01 square plus 0.7 square, which is equal to 0.0121 plus 0.0001 plus 0.49, which is equal to 0.50. Specificity is equal to reliability minus communality. Specificity of test 1 is equal to 0.70 minus 0.51, which is equal to 0.19. Specificity of test 2 is equal to 0.69 minus 0.40, which is equal to 0.29. Specificity of test 3 is equal to 0.99 minus 0.37, which is equal to 0.62. Specificity of test 4 is equal to 0.43 minus 0.39, which is equal to 0.04. Specificity of test 5 is equal to 0.53 minus 0.50, which is equal to 0.03. Uniqueness is equal to 1 minus communality. Uniqueness of test 1 is equal to 1 minus 0.51, which is equal to 0.49. Uniqueness of test 2 is equal to 1 minus 0.40, which is equal to 0.60. Uniqueness of test 3 is equal to 1 minus 0.37, which is equal to 0.63. Uniqueness of test 4 is equal to 1 minus 0.39, which is equal to 0.61. Uniqueness of test 5 is equal to 1 minus 0.50, which is equal to 0.50. Eigenvalue is the sum of squares of factor loadings over each factor. Eigenvalue of factor 1 is equal to 0.7 square plus 0.5 square plus minus 0.3 square plus 0.09 square plus 0.11 square. This is equal to 0.49 plus 0.25 plus 0.0900 plus 0.0081 plus 0.0121, which is equal to 0.85. Eigenvalue of factor 2 is equal to 0.12 square plus 0.30 square plus 0.16 square plus 0.17 square plus 0.01 square. This is equal to 0.0144 plus 0.09 plus 0.0256 plus 0.0289 plus 0.0001, which is equal to 0.16. Eigenvalue of factor 3 is equal to 0.09 square plus 0.25 square plus 0.50 square plus 0.6 square plus 0.7 square. This is equal to 0.0081 plus 0.0625 plus 0.25 plus 0.36 plus 0.49, which is equal to 1.17. Total eigenvalue is equal to 0.85 plus 0.16 plus 1.17, which is equal to 2.18. Percentage of variances is equal to eigenvalue of the factor divided by sum of eigenvalues multiplied by 100. Percentage variance of factor 1 is equal to 0.85 divided by 2.18 into 0, which is equal to 38.96%. Percentage variance of factor 2 is equal to 0.16 divided by 2.18 multiplied by 100, which is equal to 7.34%. Percentage variance of factor 3 is equal to 1.17 divided by 2.18 multiplied by 100, which is equal to 53.7%. When to factor analyze? The following conditions have been outlined by Professor B. N. Mukherjee 1975, under which factor analysis can be used. Factor analysis for data reduction can be used when the researcher wants to combine different aspects of variance related to original variables. Factor analysis should be used in test development to study the factorial structure of a battery of tests and the extent to which the test may be factorially pure. Hotelling's principal component analysis method of factor analysis may be used for deriving a set of orthogonal variables that are used in applied predications using multiple regression techniques. It can also be used to combine and scale several measures of a unidimensional domain so as to produce maximum discrimination among individuals along a single dimension. Factor analysis reveals the minimum number of independent dimensions that are required to define adequately the domain under investigation. Factor analysis preferred when the total underlying dimensions are less than the number of variables taken in the study. This is particularly required when the observed variables are infested with measurement error. An oblique factor analysis can only reveal as to what extent two or more hypothetical variables are mutually orthogonal. If this is revealed by Varimax rotation and not orthogonal, then such a result is merely a mathematical deceit. When not to factor analyze. In the past, factor analysis has been misused while using experimental variables or populations, or both. Guilford observed that scores from the Tudor preference record, Bernreuter's personality inventory, the Minnesota multiphasic personality inventory, and Guilford Martin personality inventories are inappropriate variables to use under most conditions of analysis. According to Guilford, the common faults of factor analysis are undue extraction of factors for the number of experimental variables, superfluous factorially complex experimental variables, failure of extraction of a common factor fails due to substantial representation in only one experimental variable, insufficient extraction of factors, false correlation coefficients or correlations of scores are used in the analysis, a heterogeneous population is chosen for analysis, the difficulty level of the tests often vary. Professor B. N. Mukherjee has similarly listed the conditions under which factor analysis should not be carried out. These are when intercorrelations fail to meet the assumption of linearity, if the variables are combined in a non-additive manner, that is multiplicative. Example, in the theory of achievement motivation, then factor analysis should not be applied. Factor loadings are not invariant under change of scaling units, and hence one should not compare factors from one population to another if the variables have different amount of variability in different populations. Factor analysis method is not suitable for biserial or tetrachoric correlation coefficients because the assumption that the underlying variables are normally distributed is often inappropriate. The observed coefficients are often exceptionally large. Factor analysis is also contraindicated where an intercorrelation matrix is composed of selections of correlation matrices derived from different groups. Tobias and Carlson mentioned that factor analysis should not be done for intercorrelation matrix that does not significantly deviate from an identity matrix. An identity matrix is one in which the diagonal has unity values and the off-diagonal elements are zero. Conventional factor analysis is inappropriate when applied to certain patterned correlation matrices like the simplex and circumplex included by Gutman under his index structure. Jum C. Nunnally in psychometry theory has highlighted some precautions to be kept in mind when using factor analysis. These are factor analysis should not be used when the correlation between variables is zero or near zero, as it can lead to misinterpretation of the extracted factors. Refrain interpretation of mere factor loadings to avoid overinterpretation of factors. If variables or tests are highly correlated, then factor analysis should not be carried out. Factor analysis should not be carried out when the population is heterogeneous in terms of age, sex, education, and socioeconomic status. Factor analysis should be done separately for males and females when considering sex as a variable to maintain the homogeneity of the population. One can ignore sex as a variable in factor analysis. Factor analysis should not be implemented when the number of subjects used in the study is less than the number of variables considered.
Summary. The primary distinctive element of factor analysis is data reduction. Variables that correlate highly with each other, they represent a single factor, and variables which do not correlate with each other, they are identified as either independent or orthogonal factors. In the Thurston-Centroid method of factor analysis, we try to convert the correlation matrix into the factor matrix. Now, what is a correlation matrix? A correlation matrix is usually square in nature, and the rows and columns, they are denoted by variables. Now, theoretically, factor matrix can be square or rectangular, but practically when we are forming a factor matrix from the correlation matrix, we see that the factor matrix is usually a rectangle shaped figure. The columns represent the factors and the rows represent the variables of those factors. The total variance of any variable or test is a combination of its communality, specificity, and error variance. Factor analysis can be used to combine different aspects of variance which are related to the original variables, or to study the factorial structure of a battery of tests and the extent to which the tests may be factorially pure. Factor analysis should be avoided when the variables have different amount of variability in different population, and for distance measures or proportions of agreement, as in the case of teachers assessing any student's individual performance, maybe through class test or through examinations and so on.